Energy transfer between two electrically coupled circuits. To consider the energy transfer between two inductively coupled circuits as shown in this figure, we can show of a previous figure. Okay, previous lecture. Let the two circuits be made to oscillate with the frequency omega and let IP equal to I1. IP equal to I1 e to the power I omega t and IS equal to I2 e to the power I omega t be the current in the two circuits respectively then. Okay. Then rate of change of primary current. Rate of change of primary current. Rate of change of primary current. Rate of change of primary current equal to dIP upon dt. Okay, equal to d upon dt I1 e to the power I omega t equal to I omega I1 e to the power I omega t equal to small I omega IP. Induced EMF in the primary coil. Induced EMF in the primary coil. Induced EMF in the primary coil equal to minus LP dIP upon dt, that is minus I omega LP IP. Okay, and rate of change of secondary current. Rate of change of a secondary current. Rate of change of secondary current equal to DIS upon dt, that is d upon dt I2 e to the power omega t equal to I omega I2 e to the power I omega t, that is I omega IS. Okay, induced EMF in the secondary coil. Induced EMF in the secondary coil. Induced EMF in the secondary coil is minus LS DIS upon dt, that is minus I omega LSIS. Okay, and potential difference across the capacitor. And potential difference across the capacitor. Potential difference across the capacitor C1 in the primary circuit. C1 in the primary circuit is integration of IP dt upon C1. That is integration of I1 e to the power I omega t into dt upon C1 equal to I1 e to the power I omega t upon I omega C1 equal to IIP upon omega C1. Okay. Potential difference across the capacitor C2. Potential difference across the capacitor. Potential difference across the capacitor C2 in the secondary circuit. Secondary circuit is integration of IS dt upon C2. Okay, that is integration of I2 e to the power I omega t into dt upon C2, that is I2 e to the power I omega t upon I omega C2, that is minus IIS upon omega CS, omega C2. Okay, capacitor of secondary. If the two circuits are considered free from resistance and have inductance and capacitance only, then the EMF equation for the primary and secondary respectively, minus LP dIP upon dt plus integration of IP dt upon C1 minus capital M DIS upon dt equal to 0, and minus LS DIS upon dt plus integration of IS dt upon C2 minus capital M dIP upon dt equal to 0. Okay? Substituting the value of various quantities, we have I omega LP IP minus I upon omega C1 IP plus I omega MIS equal to 0. This is equation number first. And I omega LS IS minus I upon omega C2 IS plus I omega MIP equal to 0. That is equation number second. Okay? Equation number second. Multiplying first by first by omega by ILP and second by omega by ILS. We have omega is now 1 by LPC1 equal to W1 square, where W1 is natural frequency of the primary circuit, okay, containing inductance, and LP and LP, okay, and circuit containing inductance LP. LP is inductance. Okay? LP is inductance, and capacitance C1 is capacitance of primary circuit. Okay, and 1 by L2 C2 equal to omega 2 square, where omega 2 is the natural frequency. Omega 2 is the natural frequency of the secondary circuit natural frequency of the secondary circuit. Okay, and containing L2 and C2 is the respectively inductance and capacitance. Okay, then substituting 1 by LP C1 equal to W1 square and 1 by LS C2 equal to W2 square. We get IP W1 square minus W square equal to M by LP W square IS. Okay, then and IX in bracket IS in bracket W2 square minus W square equal to capital M by LS W square IP. multiplying we have IPIS W1 square minus W square W2 square minus W square equal to M square upon LP LS into W to the power 4 ISIP, okay, or W1 square minus W2 square W1 square minus W square and W2 square minus W square equal to M square upon LP LS and W to the power 4 equal to K square W to the power 4, where K equal to capital M upon under root of LP LS. In the coefficient of coupling is the coefficient of coupling, okay. Then to simplify put W1 equal to W2, then to simplify put W1 equal to W2 equal to W0, then W0 square minus W square whole square equal to K square omega to the power 4, or omega naught square minus omega square equal to plus minus K omega square, or omega equal to plus minus omega naught upon under root of 1 plus minus K, okay. The negative sign on the right hand side has no meaning as omega cannot be negative. The positive sign gives two frequencies. WA equal to W0 upon under root of 1 plus K and WB equal to W0 upon under root of 1 minus K. These are the normal mode frequencies. These are the normal mode frequency. These are the normal mode frequency, okay. In phase and out of phase normal modes. In phase and out of phase. In phase and out of phase normal modes. In phase and out of phase normal modes from the relation IP W1 square minus W square equal to M by LP W square IS. We have IS upon IP equal to omega 1 square minus omega square upon omega square LP upon capital M equal to omega naught square minus omega square upon omega square LP upon capital M, where omega 1 equal to omega naught. Then omega naught square upon omega square minus 1 LP upon M. This is the equation number 3rd. Selecting the value of omega. Selecting the value of omega. Selecting the value of omega equal to omega naught upon under root of 1 plus K. We have omega naught square upon omega square equal to 1 plus K, or omega naught square upon omega square minus 1 equal to plus K. Okay? Then substituting in equation number 3rd. Substituting in equation number 3rd. Substituting in equation number 3rd. Substituting in equation number 3rd, we get IS upon IP equal to plus K equal to plus K LP upon M. It is clear that the right hand side of the above equation is positive, is that IS and IP are in phase, hence omega equal to omega naught upon under root of 1 plus K equal to omega A. Represent the frequency of in the phase mode. Represent the frequency of the in phase mode of the in phase mode, okay. Similarly selecting omega equal to omega naught upon under root of 1 minus K, we find that IS upon IP equal to minus K LS upon M. This is equation number 5. Okay, is that IS and IP out of phase are out of phase. Hence omega equal to omega naught upon under root of 1 minus K equal to omega S represents the frequency of out of phase mode. Represents the frequency, represents the frequency of out of phase mode, okay. Loose and tight coupling, loose and tight coupling, okay. Loose and tight coupling, In loose coupling, K is small. In loose coupling, K is small, and both the system behave almost independently. In this case, omega A and omega B are very nearly equal to omega naught. In this case, omega A and omega B is very nearly equal to omega naught, okay. In tight coupling, K is large. In tight coupling, K is very greater than in this case is very large, very nearly equal to unity, so that omega A and omega B differs from omega naught. In this case, omega A and omega B differ from omega naught by a large quantity, the peak value of current and displacement and dip between the peaks is more pronounced. The variation of current amplitude with driving force frequency omega for the different values of K is shown in this figure. Okay, first point. For K is small. First is for K is small, and 2.4. This is the first figure. For K is very small. Okay, and for second, K having intermediate value. intermediate value. K having intermediate value. Intermediate value. And third figure, for K large, it may be noted that for K small, loose coupling bandwidth is negligible. Bandwidth is negligible. Resonance occurs at one frequency. For large, that means tight coupling bandwidth is large. Resonance occurs at low, widely apart frequencies. Okay.